and maybe getting in slightly to the, the philosophy of what we're doing and how maybe we want to be doing it. I'm not going to go into too much detail in terms of specific projects and the details of those, because Pablo covered a lot of those in his characteristic, chaotic yet charismatic way yesterday. So go back to that if you want to look at some physics insights and stuff. But I do want to give you at least a little bit of insight into the types of physics that I'm interested in, because it's always good to know where somebody's coming from so you can maybe understand my challenges and my biases. And in general, the things that I'm into are studying the real-time dynamics of quantum mini-body systems, specifically with a focus on nuclear systems, and even more specifically, a focus on finite nuclear systems. And there is a motivation behind why we want to study these time-dependent problems, and that's because within a time-dependent mini-body framework, you're putting your structure and your dynamics on the same footing, and it gives you a really nice comprehensive framework to study anything that a nucleus might want to do in those characteristic timescales. Those characteristic timescales that I'm talking about ranges between 10 to the minus 22 up to 10 to the minus 20 seconds. So if you know your SI prefix, that's zeptoseconds to tens of zeptoseconds. And while I do have a big focus on reactions in this talk and also in my research, there's really a whole lot of things that you have access to whenever you're studying things from the time-dependent perspective. So reactions make a lot of sense whenever you're at the energies that I'm typically living, so low energies. But also things like the scission dynamics of two nuclei ripping apart, or how pasta phases evolve in the crust of a neutron star. These are all things that happen about at this time scale. So if you have a mini-body method that is amenable to it, you can probably study it. And most of the results that I'm showing are from time-dependent density functional theory simulations, but the mini-body method doesn't really matter. You can, we have projects in time-dependent coupled cluster, time-dependent variational Monte Carlo, et cetera, et cetera. It's more the time of the time-dependent framework in general. Now, I want to move slightly aside from my theoretical framework and the way that I'm simulating these systems and focus on what we actually see experimentally. Unfortunately, we can't take a magnifying glass and watch two nuclei collide in the lab. We instead just see sort of a projection or a shadow on the walls of some cave or experimental hall in the form of data. And one good characteristic type of reaction that has some interesting features and impact is the Humble fusion reaction. So you can imagine you have a nuclear system, in this case, a bunch of oxygens and carbon, and you just want to know, at a given energy, what is the probability that these two things are going to end up in a carbon or Z1 plus Z2 system. And you can do this for many different energies, and you see that the way that this thing evolves is a function of energy, and as it evolves, as you change those systems, there's a lot of structure there. There's some local wiggles, there's some really big dips. Sometimes the fusion probabilities are about the same at a given energy, but then they deviate pretty greatly. So there's a lot of information there in these projections, so in this experimental data, on what's actually happening down there in the actual collision. If I zoom in to one of these systems, you see we also have a pretty good situation where we have a lot of data. We have a lot of data from many different groups. So we are in what I would say a data-rich environment for these compound nucleus reactions. But they don't always necessarily agree. So this is kind of a follow-up to the conversation we were having before about, is this dip really this big? Well, this group would say no, but that is for them to debate, and maybe us to have to pick up the pieces. And there's also different error structures, for instance. So some groups have their position error very good. They know the energy of their beam. Some groups are using a different experimental strategy. So they have some intrinsic uncertainty on what the energy is going to be. And this is, like I said, one of the simpler reactions to think about. There's also reactions that have higher dimensional data. So these are examples of what are called quasi-fission reactions. All you need to know is basically you have heavier systems, they collide, they transfer a lot of particles, but they don't stay fused. Or they can, but that's a really low probability. And what you can do in this case is actually study like the angular correlations of in my detector setup, I expect to see a lot more of fragments with this mass coming out at this angle. And this is something that you can directly simulate as well. So it has a lot of information about the actual interaction, so the dynamics, but it's heavily dependent on the structure of your colliding particles too. And that's exactly what you see here. This video that I showed at the start, this is an example of a quasi-fission reaction. And this one's relatively quick. They stick together for a little while, transferring a lot of particles and energy. In some of these reactions, it'll actually rotate around a few times. So they're truly together in a quasi-compound for quite some time. And you can imagine that if this deformation was different, or if it had a big neutron skin, or if it didn't want to equilibrate protons and neutrons, you would have quite a different outcome. So those projections have a tremendous amount of insight into our nuclear many-body problem. And one thing that I also like to show, because sometimes these blobs are a little misleading, these are actual, we have some many-body wave function. It's just a lot more convenient to draw a contour instead of just showing you a big field of density. And there's also a lot more information in terms of currents and such in here too. So in a collision, protons, neutrons, they can go opposite ways, they can bounce around, you can have little currents forming. There's a lot of complexity within these nuclear evolutions. So this is great to know that there's a lot of great data, and we have very sophisticated tools to study that. But as you might imagine, some of these simulations can be pretty expensive. So if we want to incorporate this into some sort of Bayesian UQ workflow to try to extract some information out of that, then we might be in trouble. So to give you a little bit of context into how expensive these are, it really varies. So in the best case scenario, it might take a couple node hours to do one time trajectory. In the worst case, we can take the entirety of a leadership class facility down for an afternoon, simulating some scission dynamics or something like that. So it's hugely different scales, depending on the observable you're interested in and the level of fidelity. This is why we're so interested in emulators and surrogate models, because it gives us a very quick way to evaluate the properties. And it was brought up at some point of why we're interested in actually trying to replace those high fidelity simulations with a surrogate model. I think Jean-Francois said this. And for us, one of the main reasons we want to do that is because then we get access to correlated observables. So in this case, let's say you want to know the explicit linkage between two different quantities, two different observables or properties of the nucleus. You get that naturally whenever you're just putting a drop-in replacement for your high fidelity solution. And it's also nice for the flexibility of, now I can go and use this somewhere else. I can use it as a direct one-to-one replacement for my machine killing software. And Pablo already presented some perspectives on what we're trying to do in terms of emulating dynamics, but I want to say that there's a ton of great research out there specifically in emulating these complex dynamical systems. So this is just an example from Caltech and NVIDIA group looking at things that are called neural operators. And they're really good at solving these sort of hydrodynamical type problems. And preliminary investigations show that this and similar neural operator approaches or operator machine learning, data-driven, whatever, seems to do pretty good for our nuclear case too. I'd be very curious if it works well for, say, hydro simulations. No clue, but that's something that could be good to try. The approximate what? Yeah, so this is trying to replace the complex PDEs with something that you learn. Yeah, so this is directly approximating at that level. And one perspective that that I like to think about often is, where else are these surrogate models useful? So we're often focused very heavily on using these models to enable Bayesian UQ studies, and that's still really challenging to do, and we have a lot of work to do in that space. But I think that there's a lot of really exciting things that you can also think about whenever you have a really efficient replacement for a really expensive computational simulation of your quantum systems. One perspective that I like to give you is the idea of deployable emulators. So this is a project that I lead called the Bayesian Mass Explorer, and this is sort of a theory data web app that we wanted to put together to have a very easy one-stop shop for many different types of theory data from these mass models, but with a focus on nuclear masses and derived quantities from those masses. And the idea is that this is something that if you're putting together a proposal and you want to see some theory predictions, or you just want to see what the sort of global landscape of masses look like for whatever reason, you can go here and do that. But since this is a web application with a pretty flexible cloud-enabled backend, you can actually do a little bit of computation here too. It's not just a static page. And some of the things that we've been playing around with are putting our emulators up in that cloud environment. You won't find them there now because these are all very, very preliminary type things, but we just wanted to see if they were amenable to actually running in that environment. So one of the first things we did was putting these reduced basis method emulators up in the cloud, and you could go to the web app, type in what you wanted, the slope of your symmetry energy and the symmetry energy, et cetera, hit calculate, and very quickly it will solve the equations and give you the predictions of that model for those interaction parameters. So here we're just plotting out to an absurd level of precision the binding energy and charge radius, but in principle you have access to all the observables that your relativistic mean field model has. That by itself is a fun toy. It happens very fast, but you can imagine that this could be a useful learning tool, for instance. Let's say you want to go give a talk to a bunch of people and you want to say, how do the properties of my nucleus change if I change this assumption about the nuclear matter properties? And everybody can go to the web and change things around and get a more close insight into how these things are affected without having to make sure that they have a working Fortran environment on their laptops. Now, another type of emulator that you can deploy is something that's more data-driven. So this is this is a potential energy surface. So this is something important for fission. That's basically all you need to know. And these things are really expensive to calculate, so we actually don't even want to pre-compute a bunch of these, especially for different interactions. So this is where deployable emulators can also come in, where while yes, with masses, it's not a big deal to save 2,500 numbers or 5,000 numbers, whatever it is, for a few different interactions and models. If you have things that are higher dimensional, if you have things that only one person ever is going to want to look at, then you might as well just compute it. It only takes 50 milliseconds. Like just let the cloud computer do that. Yep. Cool. And another potential use case of these things is, all right, let's let ourselves be a little creative and see what does this what doors will this open up? So instead of just going and using it as a resource or as a learning tool, now you can start to imagine having some more interactive experimental design type problems. So what you're going to see here, this is a little demo that was created by one of our fantastic undergrads, Landon Buskirk. And, oh, look, it's a password. Wait till, there we go. So what Landon has done is he's put some data points just arbitrarily on this grid. He set the error bounds of those data points, and he's going to hit fit, and it's going to do a live Bayesian calibration of a very simple model. In this case, it's a line that doesn't take very long to evaluate, so doing this calibration is not a big deal. But I think that it does kind of, if you have an emulator that is sufficiently fast, and here I'll pause it so you can see the beautiful result at the end. Now, imagine that you want to know what is the impact of measuring this mass or that mass, or what if I want to reduce the error band or reduce the uncertainty on a measurement that's already been done? How does that impact other observables? How does that impact my knowledge of other physical systems, et cetera? And this is focused more on the interactive side of things. So you go there and you actually click and maybe place a few data points on your own to see where you might want to do a measurement. But this is part of a larger idea of trying to make it as easy as possible to perform these calibrations so that you can be agile in the face of new data. And so this gets into, oh, there we go. This gets into the idea of these continuously calibrated Bayesian pipelines. So this is something that would definitely be heavily impacted by these workflow type management things that Henry was talking about. You want to make it as easy as possible to do all your computation whenever there is some new experimental measurement or some change to a theory assumption, or maybe you're developing new models or something like this. And while this is something that we'd really like to do, there's many different pieces that have to come together to make this vision possible. So you have to have good emulators, you have to have a good, quick way to do calibrations. You have to be very, very careful about keeping track of what data was actually involved in the calibration, because if you don't know what fed your model, then you probably shouldn't be trusting what it's putting out. And you want to make sure that this is something that is done in a systematic way and is extremely traceable. So one of the ideas that we, or sorry, let me switch things a little bit. One of the things that happen quite often is you have somebody at some point, in this case 2015, did an excellent calibration of their mass model, and they get these nice posterior distributions, very good Bayesian UQ study. And now here I am, say at the time that I did this study is like 5 years later or 6 years later, and I wanted to use those posteriors to compute something else. So in my case, I wanted to compute a bunch of these fusion potentials, which, you know, the fact that you see this means that I did, but how did I do that? Well, looking at this, the plot that was in this wonderful PRL is not very useful. It's great, you know, I can see it. I can see generally the probability distributions, and I can see the correlations between two parameters, but I certainly don't see anything that's higher order correlations. And it's really hard to draw samples with my eyes from this posterior distribution. So best case scenario, maybe in the supplemental material, or there's a zip file somewhere on the page that will give me these samples or some samples, hopefully without any sort of autocorrelation, so that I can then use this in my own study. Worst case scenario, which is what happened in this case, I had to contact somebody, not even one of the authors because it just wasn't as convenient, and get a table that had 1,002 samples and then use that for this study on the right. So one project that we finished up last year and we think kind of addresses a little part of this, is to make it really easy to take the fruits of that Bayesian UQ labor that you've done and distribute it to people, or let people draw their own samples. And the direction that we went was to learn those distributions. You can think of it as compressing down the information that's in all of those samples into a very efficient representation that lets you draw arbitrary samples in the future. So this project was worked on, again, by STAR undergrad Landon Buskirk, but also INT's own Yukari Yamauchi, who is here in the audience. Any applause at the end of the talk, 10% goes to her. And what we used was this wonderful technique called normalizing flows, that basically you're learning a map from some random, from some normal uncorrelated Gaussian into any arbitrary probability distribution. That map exists, so that's cool, proof of existence, love it, but figuring out what that map is usually a little trickier. So we use a neural network to do this. There are other approaches, but this just happens to be the direction that we went because of our expertise. We benchmarked this on some, let's say, toy distributions that have features that one might encounter in your own UQ study. So that includes high nonlinear correlations, multimodality, and really heavy tails in the case of the student T distribution. And it works very well. Just to give you the punchline, for these toy distributions, there's not really any problem with even this very simple vanilla implementation of the algorithm to allow one to draw whatever samples they want from these arbitrary distributions. We then applied it to a calibration that we had done for a relativistic mean field. And so in this case, actually, the distributions are quite boring, but it's a little higher dimensional, so there's something to be said about it. And there, it works quite well, too, which is why I'm presenting it to you today. The nice thing, though, in the context of what I've been talking about, is once you have trained this normalizing flow, what you're left with is like a 30 kilobyte little neural network, trained network, that then you can keep track of metadata, again, keep track of what informed it and all of these things, tag it, put a timestamp, and deploy it in one of these cloud type environments. And now, for the grad students of tomorrow, if they want to draw samples from this, they go to the website, they type how many samples they want, and you get a bunch of independently drawn samples from that posterior distribution. The fact that they're so small, the fact that it's so easy to keep track of everything that informs it, also gives good perspective for doing this frequently. You have a general run that happens, every week, every month, whatever is right for you. And you can also just keep updating the one you have. And whenever it's time for a release, it's relatively easy to say, all right, here you go. The 1.0 of this RMF calibration. Now, the last thing that I want to say is it's great that there's so much effort being put into developing these tools and these techniques and applying them into different scenarios. But I think that the thing that I've noticed time and time again is what really accelerates the progress and the uptake of all of these methods is very, let's say, passionate people sharing them with the community and working actually to make it as easy as possible to implement these things into different problems. So it's where I want to switch into advertisement mode and say that this type of thing that we put together for dimensionality reduction, I'd love to see a similar thing for some UQ type problems, maybe explorations of samplers or thinking of how to put together good workflows. If you have any good ideas for what would be really impactful for your problem, you can let me know. And then we can talk about maybe using your problem as a showcase for any of these things. The other thing that I've found really helps me in at least kind of understanding what the heck is going on in the field is talking with people. And since we don't hang out very often, it's also very nice to have these sort of online spaces where you can get together and share cool papers, share cool techniques, and do it in a very low effort way. Because at the end of the day, I think that one of the big takeaways is you really want to make these things as easy as possible to use. Once you have put a big focus on the accessibility of your results and your methods, it's very likely that they're actually going to get picked up and taken somewhere new that you never even thought of. So thank you very much.